MCT4C day 20. The lesson is 3.2 components of vectors. The 3-minute review goal is to recognize and represent vectors, including those that arise from real-world applications. And essentially, we just want to read and write some vectors here, practice what we were doing yesterday. Describe this vector. It's a 25 Newton force. So 25 newtons, I'm going to say at 30 degrees to the horizontal. 30 degrees angle above horizontal. This vector shooting off in this direction, it's a velocity vector here, meters per second. Looks like it's 5 meters per second is the magnitude. The direction is at a bearing of 105 degrees. And that's all. We can just stop there because we know what true bearing means. The opposite vector, well, the opposite vector would be a vector going this way. Now, isn't it exactly the same thing? Well, not really, because we kind of think of a vector having a tail on whatever object it's acting on. So it's sort of, the tail ends up hooked up there. So it's actually, this opposite vector would be, you know, shooting it into the ground. This one's lifting it. This one's sort of pushing it into the ground. So, which is a bit weird. So the opposite vector would still be the same length, 25 newtons. And I guess we could call this angle 30 degrees, but just so we can see there, 150 degrees would be the straight line. 150 degrees below, maybe below horizontal. It's a little bit weird describing this one. This one's not bad because the opposite vector is the same length going in the opposite direction, so it's still 5 meters per second. But what are the angles here? Well, that's 105. This little angle's 15. Means this little angle's 15. And then the bearing would be 90, 180, 270 plus 15 is 285. So a bearing at 285 degrees. Parallel but not equivalent. Parallel but not equivalent. So parallel means they have the same direction. Not equivalent means, well, if they're not equal vectors, then it means it has to have a different magnitude. So same direction, different magnitude. So maybe it's 30 newtons for the first one. 30 newtons at 30 degrees above. Might have been some of your instinct to say the opposite here, and the opposite would work by the definition, but that's no fun. We just use the opposite. Maybe 6 meters at a bearing of 105. A little bit faster or a little bit slower, as long as the magnitude's not the same, would make it not equivalent. The same magnitude, but with a different direction. Well, this is pretty easy, right? Same magnitude so this one has to be 25 newtons, but at any other angle. So who knows, 60 degrees maybe? Horizontal. And this might be same magnitude in any other direction. Maybe we'll say straight east. One of my favorite directions, straight east. Okay, on to the lesson. So the expectations for today are to resolve a vector into its vertical and horizontal components. So these vectors that are sort of shooting off in any old direction, we often think of them as going, you know, straight up or straight sideways or straight east and north, and these vertical and horizontal components are important. In most applications, it makes sense to think of vectors this way. So for instance, if we had a force sort of pulling on a weight, sort of off at a 30-degree angle, there's actually 2 pieces to that force. And I'm going to Oops. Just draw them in here. I'm going to change the the color so we can see them. There's one force that's going this way, and there's one force that's going straight up this way. Change the color here real quick. That one may be green, and this one may be red. Just to keep them apart. For no, it's not stop and go colors. They're just so we can keep them apart. So when you're pulling on a weight, part of this force is going to drag the weight along the ground. The other part of the force is tending to lift it up, probably make it easier to move forward, is to lift it up. And notice if the angle changes, the components will change. So here we go. If this is the horizontal component. Remember, horizontal is across this way like the horizon. And if I wanted to calculate that, well, this is just a right angle triangle, right? This is just triangle trig. If I wanted to find the magnitude of h, well, this is the adjacent side to 30, so the adjacent hypotenuse is the cosine of 30 degrees. And yes, that's a special angle, and no, you don't have to worry about that. We're just going to pound that into a calculator here very soon. The magnitude of h over the hypotenuse, I'm going to cross multiply. And that's about 21.6, and that's in newtons. And notice that's the magnitude of this red vector for the vertical component, the component that's tending to lift the weight. We've got the opposite side over the hypotenuse, that's the sine of 30 degrees, is the opposite side over the hypotenuse. And gee, same calculation, they're pretty close, except for it's the sine this time. And even from our diagram, it looks like the vertical component, the lifting component, is less. So I would expect this answer when I put it into my calculator to be less than 21, and it is. This is 12.5 newtons. So this force that's pulling the weight at a 30-degree angle could be thought of as two separate forces, rectangular forces at 90 degrees, one that's pulling it horizontally along the ground, and a different force that's pulling it straight up in the air. And that's what we talk about as rectangular components. In the next example, it's the rectangular components are our directions that we're used to, right? The directions north, west, south, and east. In this diagram, it's pretty small, but we'll get around it. I'm going to use, because I always think of quadrant bearings, so I'm going to use the two components. I'm just going to do it freehand. Why not, eh? This component, that's making it go straight south, and then perpendicular to it would be a component, and I'm going to do something weird here, that's going straight east, right? Well, remember, straight east. Vectors, doesn't matter their position, right? This is still a vector that represents going straight east, so I could put that in the right spot there. And then this is a nice little right angle triangle where I've got two components, my south component and my east component, right? This paddle or swimming or walking or whatever this resultant vector is, whatever the person was doing, represents the same as going south first, then east. And we can see that it's going more east than south because the magnitude of the red vector is bigger, but we're going to actually calculate them. So what color do I got? I got red. So I'm going to do, oh, I got to find an angle, don't I? From this angle. So if this is 105, this little angle is 15. What's this angle? Well, we have to add up to 95. That's 75, right? So I go 90 subtract 15, that's 75. So now, from that angle, E is the opposite side. And I have the hypotenuse, which is 5. opposite and hypotenuse is the sine of 75 is this expression. Cross multiply. A lot of the same sorts of calculations, right? This is just an application of trigonometry. Pound that into a calculator. Notice that's the speed. So this person was walking 5 meters per second in this direction. 4.8 meters per second of that walk was going straight east. Similarly, if I'm thinking about the south component, well, that's the adjacent side to that 75-degree angle. That's the cos. Cos of 75 is equal to the magnitude of the south component over the hypotenuse. Cross multiply and divide. Actually, I don't need to divide, do I? Just cross multiply. Let me mess that up a little bit here. Let's do a decent job. Let's do a good job of our note here. Calculator is about 1.3. So this walk, or this canoe paddle, or whatever it is, represented the two components going east at this speed and going south at that speed. Notice if I added that, put those things together, the walk or whatever is 4.8 meters per second east and 4.3 meters per second south. Right? Those are the two rectangular components. Last example today already, I think. Draw a scale diagram of the situation. Okay, that's going to slow us down a little bit. But if I had an 80 kilometer an hour hit, the angle 60. So I'm going to draw the ground here. Oops, maybe I don't want that. The ground shouldn't be a vector, I don't think. So I'm going to make that not have a square ends. There we go. Yeah, ground. And then this vector is shooting off at a 90-degree angle, and I gotta do it to scale. So I'm going to pick maybe a scale of 1 centimeter, and this is a lot. So maybe 1 centimeter equals 20 kilometers per hour, and then I'll draw the line off at an angle of 60 degrees. That's 4 centimeters long, right? So okay, so I can need a couple of tools here. I need my protractor. Make that maybe a little smaller. Can I make that smaller? It'll be fine like that. And then my ruler. There's my ruler. All right, so I'm going to move this into place. There's protractors in the classroom for you to practice this sort of thing. You will be asked to do this. 60 degrees is there. It's the acute angle, so I'm going to put a little tick there. It may not, I might not have to be that long, but I'm going to set the ruler up to do that. And look what I found. Oh, look what I figured out how to do. Right? Yeah, nice. Okay, and then my vector is going to be, I said 4 centimeters long. At that angle of 60 degrees. But now I want to resolve it into, I think, or was it say, draw a scale diagram. Okay, there's my scale diagram. Done. Dandy. It says, use trig to resolve the velocity into horizontal and vertical components. Okay, so part of this baseball hit was to go straight along the ground, and the other part was a straight pop-up, right? So we've got a horizontal component and a vertical component that meet at a 90-degree angle. So I've got a vertical component and a horizontal component. And I'm going to calculate these, right? We said that this was 60 degrees, and so now I can find these. If I wanted the hypotenuse, that's the, or the h, the horizontal rather, that's the adjacent side, so it's the cos of 60 is the magnitude of h over 80. Cross multiply, and that answer should be, I think, 40. And that's kilometers per hour. And then this component, the vertical component, this is the straight pop-up component, is the opposite side. The sine is magnitude of v over 80, cross multiply, plug it into a calculator, and that is about 69.3 kilometers per hour. And so that hit had those two rectangular components. This is a bit of a strange question. It says, use your scale diagram to check your solution. A nice thing about a scale diagram is, since I drew this to scale and I drew the angle right, one method of answering these vector problems is just to measure it, right? So one thing I could do, for instance, for h, well, it looks like the component is about 2 centimeters long, right? So if I go h, the magnitude of h, which was 2 centimeters, but I said each centimeter was 20 kilometers per hour, so I got to multiply by 20 kilometers per hour, and that's, that's bang on, and nice, yay, happy face, kilometers per hour. This other one, the vertical component, let's try it. Vertical component. Turn my ruler here. All right. Measure it. What would you say there? About 3.5, maybe 3.5 centimeters. About, if I stop wiggling my ruler, it looks like about 3.5, maybe 3.4 centimeters. But each centimeter is 20, so that makes, what's that? That's 68 kilometers per hour. And we weren't bang on, but it's pretty good. Notice that if these were way off, I'd be wondering about what I did wrong. Okay? Okay, that looks like it might be it for the day. Okay, good luck with day 2 of your vector homework.